But at the end of the stack, what it will tell you is the peak that came out of the HPLC as a single peak actually contains two compounds which has a mass of 100 and 200, because mass spec can recognize the mass of the compound. They may have two compounds, they may have the same UV absorbance, they may be coming out within the same peak, but they would have two different masses. So if you have a mass detector coupled to the stack of your HPLC, you can actually say that this contains more than one compounds. That's an example of method development using a single quad. One of the most important analyzers today, whether it's pharma, non-pharma, or basic research, is quadrupole time of flight or time of flight racetrack. What does it tell you? This picture shows that if you have three cars which are different, they start from a common point with a constant kinetic energy and move across a certain length. So the mass which is heavier is going to move with a slower velocity, to move with a higher velocity, and that's how they get separated based on their masses. That's a very, very simple representation of the time of flight analyzer. There are two kinds of time of flight analyzer. One is a simple TOF. TOF stands for time of flight. So the simple TOF, which is the LC-MS instrument, which does not have the fragmentation capabilities. But if I add a quadrupole and a collision cell into it, I get fragmentation capabilities. So what is the importance of having TOF and accurate mass? If I'm able to explain this slide, I think I've come to the end of my presentation. What is the accurate mass? We all know that the mass of hydrogen is 1. We always say it's 1, but it's actually 1.0078. Similarly, nitrogen, it's 14.003. And oxygen, we always call it 16, but actually it is 15.9949. It is this fractional mass that I'm talking about. If there is an instrument which can recognize the fractional mass, or which has capability to measure the fractional mass between two compounds who undergo a modification. The table, the bracket that I've shown besides this slide is, if you have a compound and you do a chemical reaction, it could be metabolism, it could be degradation, it could be whatever, and it loses a mass of 16. So what do I infer from that? I infer that has it lost an oxygen or has it lost an NH2 group? Because both of them have a mass of 16. So if my instrument does not have the capability to measure the fractional masses, I will not be able to tell whether I've lost a 16 or I've lost a NH2. But if I look at the exact mass of these moieties, I see that oxygen is 15.9949 and NH2 is 16.0186. These accurately at one single go, I can say that because of this reaction, my compound has lost oxygen or NH2 group. So that is the importance of accurate mass. It is applied everywhere, whether it is impurity profiling, whether it's metabolite identification, or even proteomics. When you're trying to identify proteins, you make use of the accurate mass. These are some of the applications that time of flight would get applied to: combinatorial chemistry, metabolite identification, impurity profiling, proteomics, like I said, and then also natural synthetic product identification. So basically, there is no analytical area which can go unexplored using a time of flight analyzer. This is a workflow. You basically do a LC-MS analysis. You find all the compounds that are in there and straight away go for identification. Or if you want, you can actually do comparison between sample sets. So you have 10 samples and you can do actually comparisons between these sample sets. So the next few slides I'm going to skip through because that's not very relevant, but this is an example of of impurity profiling. This is a drug which is getting synthesized or manufactured, and which comes out on the chromatogram as the main compound, the tall peak. The other ones like D, A, C, B, F, etc., are the impurities which are very low in intensity. So out of these, E and F were identified because they were the unfinished, starting which was unfinished. But compounds A, B, C, D were taken to MS and we measured the actual mass. So the actual mass of the compound here, the main compound is 264.1964, and the impurities, A has a mass of 957, which actually shows that it's an isomer. It's an isomer of the main compound with the same empirical formula and mass. Impurities B and C result from a loss of water, and impurity D results from the loss of the methyl group. So that's the importance of accurate mass. I just put this onto the did a MS analysis, calculated the actual the exact mass of the compound, and was able to identify what modifications it has gone through. So because I represent Agilent Technologies, I work for Agilent Technologies, it is my responsibility to tell you that Agilent Technologies has all the available mass specs that a pharmaceutical company or any analytical lab can use. We have a range of QTOFs, ion trap and time of flight analyzers, and of the quantitation applications we have the triple quadrupoles and the single quadrupole instruments. So that's the software. You have the instrument control software, you have the qualitative analysis and also the quantitative analysis from your LC-MS data. That's the workflow that we follow at Agilent for analytical applications. You acquire data, then you find everything that is there in your sample. You can easily compare samples, or you can go straight to identifying the compounds, and everything is automated. You basically have done nothing except preparing your samples and putting them onto the mass spec. You have an automated HPLC which injects the samples, does the analysis, sends it to the mass spec. The mass spec acquires data, processes the file, it takes out everything that is present in your sample as compounds, and then tries to identify them using, if it's a protein, then it's a protein database search, or if it's a spectral library, you match it with the spectral library. So at the end of the run, what you get is a list of compounds with a certain degree of confidence that the instrument or the software has for identifying them. So coming to the last, I think the second last slide, conclusions would be mass spectrometry as a technique. It basically finds applications in almost all the areas of science. Whether you look at metabolite identification, you look at bioanalytical applications, look at proteomics, metabolomics, whatever, you would find a mass spec or mass spectrometry as a technique with your analytical requirements. Different platforms of mass spec, they basically cater to different applications. If you remember the second or the third slide, wherein I showed you different mass specs and so if you move from qualitative to quantitative applications, you'll see that there is a certain shift in the technologies. So, basically, what is the kind of information you want from the sample? Based on that, you choose the analyzer. And then a good thing is hardware produces a large amount of complex data which needs to be interpreted by advanced softwares. In the last 15-20 years of my mass spec career, what I've seen is a little improvement on the hardware, but more and more improvement on the software. Something that is going to make sense out of your data. You have good data coming from a good hardware, but if you have a lousy software, you basically go nowhere. You just can't make head or tail out of the data. So the advancements have been more on the software side rather than the hardware side. Okay, so With this, I come to the last slide, which is one of the most important slides. And basically to thank you for the attention that you have given. And I would take any questions.